Alright everybody, this is going to be a simple example using we're going to be generating cost functions for a very simple multi-layer perceptron that recognizes handwritten digits from the end of this data set, and this is an example using a convolutional neural network, but they're very similar, but I'll probably go over this one a little bit. So here we go, we import all of our libraries. We're using the deep library for the genetic programming. This is a pretty good library. I didn't really look too far and wide for genetic programming libraries, but this one seemed what most people use. It's very customizable compared to the other ones I've heard, so yeah. I honestly have no idea what this does. I don't know that much about TensorFlow, and I know some people, whenever they have problems, they enable this and it fixes them problems. I just have it commented out in case anyone wants to use it. I was, I guess, messing around with it while I was doing this, but this version runs just fine with it commented out. And yeah, you guys see this. I don't need to read that out. So all these functions are the primitive set functions. These are the functions that we'll be making our cost functions out of. So if you wanted to have, these are like the kind of mini sub functions. So if you wanted to have like cost equals y minus y hat squared, you would need a minus function, you would need a square function, stuff like that. So those are what these are, and these are just small numbers added to some of the functions just to make sure that there's no division by 0 or anything, or there's some weird stuff that can go on with logarithms, stuff like that. So, and I just used a bunch of TF casts on these just to make sure they're all the same data type. I'm sure this is not necessary, but I was having some issues, like in the middle of runs I would get some error like, oh, you divided a float 64 by float 32, and I was just like, okay, I'm gonna leave this running for 16 hours. I can't afford to have it mess up at hour 10, so I just put float 32 on everything. I'm sure this is not necessary, but it works just fine. If you guys who know more about TensorFlow than me, which I'm sure a lot of you will, you guys can take this off if you deem it's unnecessary. So yeah, another thing, it's important that all these functions are differentiable by TensorFlow. So since we're making cost functions, TensorFlow needs to be able to differentiate these functions. And yeah, that's why I'm using like TF add. You don't actually need TF add because TF recognizes the regular Python symbols, but I was just being more explicit. And yeah, I just use TF functions, power and stuff. You can also use Keras backend functions. And yeah, since we're doing on the MNIST data set, here's just MNIST stuff. I'm not going to go over this. Now we add all the functions we defined earlier into the primitive set. So this number here at the end of these is how many inputs each function takes. So obviously multiply and subtract stuff take 2, and square and all these other ones take 1. So I'm not going to explain that too much. Renaming arguments, ephemeral constants. If you guys know what if you know genetic programming stuff, you'll know what that is. It's basically just adding random numbers into the functions so we can have some constants. Yeah, this tuple may seem weird, but as the comment says here, deep needs this to be a tuple. And yeah, this is just creating the fitness class. I think it's the fitness class. I was a bit confused whether it's the fitness class or a fitness object. Based on what I've seen, I think it's the fitness class. And same thing here with the individual class, I think. Yeah, this is just deep stuff. I'm not going to go over all the nitty gritty deep stuff. Like, if you watch this video, you won't learn how to use the deep framework just because I can't explain it in a whole video. It probably took me like, I don't know, probably 6 to 8 hours or something just running through deep documentation just so I can make this pretty simple program. So it's not, I can't explain it in this video. And more deep stuff, these just registering functions we're going to use eventually. In deep, you need to register certain functions for some reason. I'm sure it's, I say for some reason like it's a bad thing. I'm sure they had a good reason to do this. And here's a very important function, is invalid. In deep, I couldn't figure out how to put restrictions on functions or on functions that you generate. So an important thing with the cost function is you can't have since Keras requires that all custom loss functions they only take in two inputs, y and y hat. If deep generates a function that only takes in one input, then Keras will freak out. So this just makes sure that all the functions will have two inputs. Well, this itself doesn't do that, but you'll see how this is used. One could argue, okay, just make it take in two inputs and just don't use one of the inputs. That way Keras doesn't freak out. And I'm sure that's that's probably the optimal solution, but I didn't think of that at the time, and this is what I have. So I'm sure you guys can implement that. Either way, I don't think that much would change. This technique is probably arguably faster or more optimal. So here's the big important function. This is like the main. This is the big useful part of this of EEFs. So before we do anything, if the individual is invalid, we return 0. And you guys see here, this needs to return a tuple. So that's why we have that. So and then if it makes it past this little check, and returning 0 is the fitness here. So it gives this individual fitness of 0. So, and then if it makes it past that, we do cost function equals toolbox compile expression. And then it's just printing the individual so we can see what's going on. Now we build a Keras model. I'm sure you could probably build the model outside of the function. That way you don't need to keep building the model every time, but I don't know. It's actually not that computationally expensive, and this was just easier. And using the atom optimizer, and loss is our custom loss function up here. And we measure accuracy. Then this example, I'm doing one epoch just so you can see what's going on. You can, of course, do multiple epochs. And now we evaluate the model. And then we want to delete the model in kclear session. Maybe you only need one of these actually, but this is just so we don't, I mean, in this whole run, we're going to train like over 100 models, and we don't want extra models just sitting in the background unused. And before I had this, the models would take exponentially longer to train. So I'd have one model take 30 seconds, next one take 31, next one 32. So this is, at least one of these is necessary. Then you print the accuracy of the model. And this is just for my convenience, kind of. So, or maybe it may help with the algorithm, but this isn't necessary. But I just like working with a bit larger numbers, so so it's nicer. And then so this is actually a really important line. Fitness equals validation accuracy times whatever you want. But yeah, that's how we're assigning the fitness to each cost function based on how well a neural network performs using that cost function. And you can measure performance by a bunch of different ways. Like this could be validation loss, it can be train loss, it can be a bunch of stuff. It can be like you could do it so it rewards cost functions that pass a certain threshold and the least number of epochs or something like that. You can measure this. This can be a bunch of different things. And this is just an example on a deep learning model, but you could do this on, I said in the other video, in the introductory video, that you can use EEFs for genetic algorithms, genetic programming. You could use an EEF to generate this function for another genetic programming. Maybe not the whole function, but technically the whole function, but you know what I mean. So you can use EEFs to generate an evaluation for a function for another genetic programming model, or you can do this for machine learning models. This can be so many different things. And then we return fitness as a tuple. And this is more toolbox stuff. It may seem weird to have registers on either side of this evaluation thing, and it probably is, but this is how they did it in the deep documentation. And then this is an important thing. This makes the trees, it makes the height not go past a certain limit. And John R. Koza, he said in his book, in one of his books, I guess, that 17 is a good thing for this, but I think he said that in like 1994 or something, so maybe they found something better. And if you don't know, John R. Koza he spent a bunch of time and he's written a bunch of books on genetic programming. I don't even know if this actually works, because when I generate some trees, they have very big, I feel like they're deeper than 17, or maybe I'm getting height and depth confused, but I don't know. Random seed, and we initiate the population, or initialize the population. We want 100 individuals, and Hall of Fame. This just says, hey, keep track of the 10 best individuals ever, no matter what generation they're in, and store them in, I guess, a array or whatever they choose to store it in, probably an array. And this is just more deep stuff. This will kind of print out a little digest after every, I don't know if this will print it out, but something with mstats will print out a little digest after every generation and tell us what's going on. And here is the main thing. This is what gets it all going. And yeah, this is pretty self-explanatory. I think so. You'll notice, like, okay, well, if there's a 50% crossover probability, 40% mutation probability, where's that other percent going? And I'm pretty sure deep automatically fills that extra 10% with the reproduction operation, which just clones individuals into the next generation. And then here we just print out all the Hall of Fame that we kept track of. So I actually probably should have started this while I was explaining it, but we can start it now. All right, we're back. I guess Anaconda was freaking out because I made copies of these and put them in a new directory. So you guys are gonna see the kind of the older one that is, I think it's actually pretty much identical to this. It just has a different name because I'm naming them what they should for the GitHub repository I post on this. But yeah, these are identical. Maybe the comments are a bit different, but yeah. So let's run it. Hello? here we go. So it's training models, and this one had a very bad accuracy on the validation set. So it will print out the function that it used, and then it will train the model with it and print out how well the model did on the validation or the test set. Sorry about that. So, yep. We can, well, that one did terrible. But yeah, we're getting some really good ones already. And if you see one of these you like, you can just you can copy it, and you could remake that cost function yourself. Here's a little digest of generation 0. But yeah, so of course these cost functions will start to get a lot better during the as the generations go on, and at the end it will print out the Hall of Fame with the 10 best cost functions. You can of course write this to a file or something, whatever. And yeah, you can see some of these are doing really good. Like this one has a 96 already, and here's the cost function. Like, who would have thought this would be a good cost function? And some of them are really bad, but eventually they'll tend towards being good. But yeah, let's hop into the convolutional neural network one. I'll be right back. Alright, we're back. This is pretty much identical code, except, well, there's different imports, but they're just different TensorFlow imports. Pretty much identical code, except in here, in the evaluation function, we have this big old juicy convolutional neural network instead of that weak regular network we had. So yeah, let's close this. And this is identical to this one that will be in the GitHub repository, just different name because Anaconda is having a fit, I guess. This one will take, of course, slower to train, but you'll see it. But yeah, while this is going, I'll talk about some other stuff about these. So one kind of cool thing that someone could do is I want to have a max function in this primitive set. Well, there's a bunch of functions I want to have in this primitive set, but obviously TensorFlow can't differentiate certain functions, and I think the max function falls into that category. So maybe if you really wanted to, you could make your own auto differentiation system and have the max function be defined. That's a lot of work, but if it improves it, improves it. But yeah, if you're if you didn't watch the previous video, the introductory video, then on this example, I managed to get cost functions that performed better than categorical cross entropy and squared error on the MNIST data set. And that kind of shows the worth of this thing. It came up with cost functions that are better than some human-made cost functions for this task in like 3 hours, as opposed to however long it took humans to come up with categorical cross entropy. And yeah, and I just found out what genetic programming is like a month ago, so I'm sure if someone who actually knows what they're doing does something with this, I think it's fairly a straightforward path to beat the benchmarks on things like the SciFar data set and just a bunch of other common data sets, because yeah, the only reason it wouldn't work is if humans have themselves came up with the best cost function in the world, and I think it's very unlikely that categorical cross entropy is the best cost function we'll ever have. So yeah. Anything else? I'll wait for this to be done training. I don't know if there's anything else. If you have any questions or anything, I'll have a bunch of my info in the description. I'll answer comments to this video. If you want to collaborate and try to beat the record on this or something, then feel free to let me know. And there's one thing I wanted to say. I forgot what it was. But yeah, these things like these hyperparameters, I know nothing about genetic programming hyperparameters. So stuff like this, maybe even tournament selection, is just a bad thing to use here. But yeah, if any of you who knows about genetic programming a lot better than I do, or even a little bit better than I do, wants to do something with this, go ahead. Right, everything will be on GitHub. And yeah, these are supposed to, it doesn't matter, but it's gonna bother me. And wow, this one got exactly 0. But hopefully this cost function will do better. I'm gonna end the video, but because this one's gonna take forever. But yeah, thank you all so much for watching. I'll have my info in the description. And yep, this will be on GitHub. Though if you're just seeing this video very early, then there'll be a little bit of a delay before it's on GitHub, because I need to add the link to the video here and stuff. But yeah, bye. Alright, one quick thing that I noticed that I left out is I didn't talk about how it's kind of almost applied, but this kind of technology or algorithm, it will cater the cost functions you're making to whatever task you're doing. So you can make cost functions that are specifically catered to, for example, this model, or a recurrent neural network or something like that. So that's sometimes a desirable effect, sometimes it's not, because sometimes you want to have a cost function that can be used for everything, and sometimes you want to have a slightly better cost function that's specifically tuned for a certain task or model. And it's just an interesting thing to note. You can also, one thing I didn't talk about is, right now I'm only using one model's performance on one data set to decide what the fitness of the cost function is. But you can train multiple models on multiple different data sets in here. So if you want, like, I guess like a super computer vision cost function, you could train a model on the SciFar data set, you train one on the MNIST, you train one on Fashion MNIST, and you can take into account the results from all of those models training into the fitness calculation. So you could say, like, fitness equals this plus whatever weight you wanted to use, just a random number, and then you could do validation accuracy 2 or something like that. You could do that for a bunch of different stuff. So I just figured an interesting thing to note. And these functions are actually, the cost functions I use are pretty transferable. So I used this model to generate a cost function on the MNIST data set, and then I just used that same cost function I generated on a convolutional neural network, and I managed to get within like 0.15% of the world record benchmark on MNIST, which I think is the one that was the performance in the Drop Connect paper. So yeah, the functions are, from what I've done, I've found them to be fairly transferable. And okay, that's it. Bye, everybody.